Alright, hey guys, what's going on? So today we are going to verify the unified conformal algebra. So in the last video, we were able to prove all of this. We were then able to show the generators for this unified conformal algebra, but now we're going to see that these things obey a very interesting structure to them that's very reminiscent of a Lorentz algebra, okay? So with that being said, make sure to hit that like and subscribe button. Make sure to go onto my Patreon page if you want to support the channel. Again, if you support the channel, you get not just access to conformal algebra, but everything else that I'm offering as well. So, without further ado, let's go ahead and get started. So if we go back just all the way to the beginning really quick, the whole point of this conformal algebra enterprise was to take a look at the physics of things under a transformation of a coordinate system. And our coordinate system, we could say, had time and some spatial component, and then we can rotate, or we can translate, or we can dilate our coordinate system. Excuse me. So our new coordinate system could be something like this, t and x, and the difference between our two coordinate systems then was given by this epsilon. Okay, and the epsilon we found it was a vector. We could see it's a vector, and it had some components to it, e mu and e nu, and we found that the relationship here that mu d nu, the sum of these two guys was equal to 2 over d, this was dot epsilon, right? I'm just double checking, not messing things up with our Minkowski metric, and that's just gonna be mu nu, right? We found that this was this was the equation that dictated the rules of the dynamics of this epsilon, or not the dynamics, but the rules that this epsilon should obey. Okay. This was our conformal. This is a conformal algebra, or conformal field theory really comes from this equation, right? So this equation here is really the big granddaddy of all of conformal algebra. That's something that you kind of just have to know, or at least type up somewhere on your computer, just like I have, and have it like burnt into your memory if this conformal field theory is actually something that you're very interested in getting into. This is like the opening the floodgates to conformal field theory. We did a lot of manipulations, and we were able to derive all of these different types of transformations that we're able to do on our coordinate system. One was our standard translations, right? So you can move the coordinate system, you can dilate the coordinate system. That corresponds to stretching or squeezing in some direction. And then we can do this guy here, right? This is rotations, or Lorentz transformation. So this is rotations and boosts, right? So we have these guys, but then we found out that there was also this weirdo, and this weirdo here also came from our analysis of this right here, which is quite interesting, right? Because it's not quite obvious exactly what this does, what exactly remains invariant under these types of transformations. We haven't really talked about that yet, but we're going to. And this is just a really weird thing, right? The idea here being that this is a new thing that emerges out of this equation. This equation being, again, our conformal the thing that sort of starts everything with conformal algebra, and it really tells us something about this epsilon. Okay. All right. So we have these. We're then able to package all of these guys into these generators here, and these generators here we found we were going to find obey this relationship right here. So let's go ahead and show this now. We're going to show it generally. Okay. And the idea here is that this here is very reminiscent. It quite reminiscent of Lorentz algebra, the Lorentz algebra. I've gone over Lorentz algebra before in my quantum field theory playlist, but nevertheless, this has the same structure. When we look at the indices, it's going to be the same. So our generators here obey Lorentz algebra when they're packaged in this way. And you can sort of make sense of this almost kind of intuitively, maybe at least a little bit, by saying, okay, well, this thing has two indices, this thing has zero indices. So we'll say, okay, this guy, two indices here, two indices here, but zero here. Okay, that doesn't make too much sense. But maybe we can combine these two one index guys. Okay, and when we do that, we'll stipulate these two things. Okay, that's it. Right on the face of this looks arbitrary and weird. Not totally sure why we're doing this, but we'll see why we're doing this in a bit. Okay, so let's go ahead and get started. So one of the things we also have to note, that we also noted before, is that we have this guy right here. All right, so this guy right here, and these guys, we now have two time-like components. This is kind of strange, right? This is a regular time-like component. This is eta, tt, and then everything in between, well, that's going to be the diagonal portion of our metric, and then this is the last diagonal portion of our metric. The idea here is that these two guys are typically usually suppressed when we're not talking about conformal field theory. When we're talking about just standard quantum field theory, we have these two guys, and we're dealing with those. So this whole new thing opens up to us, these two guys here. So so let's go ahead and with these identities show that our newly formed generators obey this relationship. Okay, we're going to start off with J mu nu. Here's J mu or M mu nu, right? So that's going to be this guy, right? This is M mu nu, right? So this guy and this guy are the same. You'll see that in different textbooks and sources online. Here J d alpha, right? So we're just changing d or mu with alpha. So that's just going to be, doesn't really matter what the order is. So we have of the indices. It just matters that if we have one d here, right? If we have one d, then we have if we have d without a plus 1, in other words, we have this, the addition is going to go in here. Okay, if we already have a plus 1 here, then we need a minus 1 right here. Right? Okay, so again, it seems arbitrary. Why? We're going to see why in just a bit here. So we can distribute then, because our brackets here are they're linear in that respect. And so when we distribute, we get these guys. We can flip sign. Then by flipping sign, we flip these guys. But we've calculated these guys, right? These guys are just these guys right here. And we've seen that before, right? That we've seen that we've actually calculated these, right? We've calculated what these commutation relationships are. And by doing that, we got these guys. And this was like 2 videos ago. Okay. And then then we can just repackage, right? So we get P mu, K mu, or K mu right here, and then our eta alpha mu. And so we get, that's this guy right here, right? So this guy here and this guy here, that's this right here. And then the other terms go over here, right? So these guys. All right, so now we can take these guys. Okay, so this guy here, which is what we wanted to calculate, is equal to this, right? We can verify this now with our unified form of the conformal algebra. We could say, well, we just rename the indices, right? If we go back here, we rename the indices, right? We have mu nu d alpha, so we just rename m for mu, n for mu, and then P for D and Q for alpha. We do all that in here. And what we get then is going to be this guy right here. All right, we can see that these guys are going to cancel because J mu nu again is just mu nu, so mu alpha, nu alpha, these guys are essentially going to be the same, right? Because this is just this guy right here, and so they'll cancel. So we're left with equation 1, right? So here's equation 1 here. So that, because we have this right here, which is right here, and this right here, which is right here. All right, it's a difference between the two, right? So it's a difference between the two. So now, excuse me. So we have this, okay, so we got this guy. We were able to verify it now. So let's do the other example. The other example is mu d with d and d plus 1, right? So that's going to be, excuse me, mu d and d plus 1. So we have the dilation and this guy right here. Okay. So the dilation then is here, this guy, and then this one right here is right here. Again, we distribute, and then change sign again. We've calculated these commutation relationships before. It's just these guys. And then from here to here, we just factor out the I, right? So I, that's going to be negative. This guy's positive because there's two negative signs. And so negative times negative is positive, which is what gets us this. So we have this. And then we get this, right? Because this guy here is just 1/2 p mu minus k mu, which is right here. Okay. And then we have, so we can verify this again with our conformal algebra, and we get this guy right here, right? Because these are just off diagonal, so the Minkowski metric, or not this one, right? This one is left as a diagonal, but we know here, right here, right? No, this one, right? That one, not this one. So this one right here, that's going to change the sign here. And also these signs also change, right? These signs also, they change. That's why we got this guy up here. Anyways. All right. So, okay, so we have verified this guy now with our conformal algebra. So we can see that when we plug these in and we do the chug in here, and then we can actually confirm it with this here. So that's really just like how you can verify this conformal algebra. So we have the generators now for this newly repackaged form of our conformal algebra. What I'm going to do now is I'm going to move on to the members section, where if you are a member for this channel, you'll be able to see the rest. If not, you can go ahead and become a member on Patreon or here on YouTube. And by doing that, you get exclusive content, again, not to just conformal field theory, but everything that I'm going to have to offer. And I'm coming out with a lot of stuff, right? I have a lot of ambition, and I've been in science for a really long time, and I want to teach this advanced science in this very unique and very accessible, hopefully easy to understand way. So with that being said, I'll see you guys in the next video. Make sure to hit that like and subscribe button and become a member if you want access to everything here.